Hi, my name is Tim Rupert, and I am a professor in the Department of Materials Science and Engineering at Johns Hopkins University and director of the Hopkins Extreme Materials Institute, known as HEMI. I received my bachelor's degree in mechanical engineering from Johns Hopkins and earned my PhD from the Massachusetts Institute of Technology. I was a professor at UC Irvine for 13 years before returning to Baltimore and JHU in 2024. My research group does a little bit of everything. When I was an undergraduate student at Hopkins, I worked with Professor of Mechanical Engineering Kevin Hemker on electron microscopy and the characterization of mechanical properties. And then, in my PhD, I shifted to studying alloy design and materials processing, and even some computational material science. My lab now employs a combination of all of these techniques. Generally, we will use whatever tools we need to solve a problem. One of our primary focuses is to investigate defect-dominated materials, particularly nanocrystalline metals. Defects often control how a material behaves, and we want to design, plan, and predict how these defects form and evolve in different alloys. We also study how dislocations, a type of one-dimensional defect in crystals, can result in defect phase transitions. If we can engineer the properties of these features, we can find ways to increase strength, strain hardening, rate sensitivity, and other complex properties. We want to move away from just living with defects and instead harness them so that we can improve materials and alter how they're made. Sometimes we lead with experiments and then use computational methods to understand the mechanism behind the behavior we just observed. And other times, we use computations to tell us which experiments to run next. Our work always flows from the desire to discover something new and testing key hypotheses related to that new idea. Rather than focusing on one method, we use a variety of tools and techniques to solve scientific problems, all at a very high level. One of these tools is machine learning, which we often use to analyze data and predict future outcomes, as well as enable new types of computer simulations. At the same time, we try to stay rooted in reality and consider the real people that are affected by our work and the uses it would have. We don't want to make something that only stays in the lab and never affects the outside world. We think about scaling up and commercializing our discoveries, with an important example being my co-founding of Foundation Alloy in 2022. This is a company that designs and manufactures novel metal alloys, working on a much larger scale than an academic lab, and at the same time interfacing directly with customers. I returned to Hopkins largely for the opportunity to lead HEMI and create a team of scientists to tackle different types of materials in extreme environments. Hopkins is deeply interconnected and fosters interdisciplinary teams across departments. We regularly have 3 to 4 disciplines working together, doing more than we could by ourselves and coming up with ambitious solutions to grand societal challenges. I'm excited to bring together larger groups to tackle the most important materials problems that the world faces today.